Now onto the one we probably think of a lot when we think of endocrine and this endocrine system and endocrine disorders, and that comes to the pancreas. Now we're going to focus on only part of the pancreas for this because the pancreas is a little bit of a dual purpose organ. We're going to focus on the pancreatic islets, talk about the different islet cells and what they do. We'll talk about insulin as well as glucagon and how both of those play a role in maintaining blood glucose levels. And then, of course, we got to talk about what happens when those things go wrong, which will lead us to one of the biggest conditions that we think of. We think endocrine, and that is diabetes. So let's remind yourselves of the pancreas. The pancreas is this organ here we see in beige. Some people say it looks like a fish. I don't honestly see it. If anything, I think it looks like a fish stick. But so be it. You may hear it called, called fish-like. But it's this organ here. It hangs out kind of like behind the stomach. And it's going to have both endo and exocrine functions. So like the acinas or the acinar cells are going to be exocrine. Those are going to deal with digestion. So we'll talk more about that function when we get to the digestive system. So we're not going to worry about that just yet. So just know that those are there. Remember that they're there, but don't get caught up in the details about those yet, because again, we will get there when we get there with digestion. We're going to put our focus on the second type of cells, and those are the islet cells. So the islet cells, if we look down here, we see all these little kind of circles. If we look at this picture, how these little kind of islands that look lighter, right? Those are going to be the islet cells, right? All these other ones that are in darker pink are going to be the acinar cells, and we're not worried about them right now. So the islet cells are going to be the endocrine tissues, the endocrine-based cells that are found in these clusters, and there's different types of cells within these islets. We have alpha, beta, and delta cells. The alpha cells are going to produce glucagon, the beta cells produce insulin, the delta cells produce somatostatin. So this is where all the hormones are coming from, are the islet cells. You will need to know which cells produce which hormones, alpha, beta, and delta. So that is something I would definitely study up on. So let's go ahead and get into these hormones. So let's start with glucagon. I like to remember it as when your glucose is gone, you need glucagon. And I know that's silly, but maybe that helps you remember. Glucagon from the alpha cells is going to be released when you don't have a lot of glucose in your blood, right? So glucose levels in your blood have dropped below normal. Maybe you have exercised a lot lately, so you used up a lot of glucose in your blood because of exercise. You may have had a meal that was very protein heavy. So those are things that could tell you to release more glucagon, because all of those things, right, mean you're not going to have as much glucose in your blood. Whereas somatostatin and insulin will stop glucagon secretion. Now, the purpose of glucagon, when we release glucagon, is to bring your blood glucose level from low to high, to bring it back up. This happens by glycogenolysis in the liver. It can be through gluconeogenesis in the liver, right? Basically, it's like, hey, we need to get glucose from somewhere. Either we are going to break down the glycogen we find in the liver, or we are going to make new glucose by, breaking down maybe like fats, fatty acids, something like that, to make new glucose molecules. Now, the one you're probably more familiar with is the one in the middle, and that's insulin. Insulin comes from the beta cells. This is when you have higher levels of blood glucose. So if you have a high level of your glucose in your blood, if you have acetylcholine that is out there, certain amino acids can stimulate this. Glucagon, GIP, growth hormone, ACTH, these can stimulate the secretion of insulin, whereas somatostatin will inhibit. And the whole point of insulin is to take a higher level of blood glucose and lower it. It's going to help the cells take glucose in. So cells cannot just take glucose in willy-nilly. They need something to help them. Insulin is that signal that allows cells to bring glucose in. It's also going to be for glycogenesis, which is the formation of glycogen in the liver, as well as in the muscles. It is going to decrease the breakdown of glycogen, and it's going to decrease making new glucose because we already have enough. And it's going to increase the formation of fats, lipogenesis, right? Making more fats, as well as proteins. So glucagon and insulin, if we look at them, they basically act opposite of each other, right? Glucagon is going to raise blood glucose levels. Insulin is going to lower blood glucose levels. And then somatostatin is probably the newest one, the one you're least familiar with. This is basically going to inhibit both, right, glucagon and insulin, and it's going to slow the absorption of nutrients from your GI tract. And so the pancreatic polypeptide is going to inhibit the secretion of that. But somatostatin, right, is just basically slow down the absorption, slow down everything when it comes to the blood glucose and absorbing more glucose from your foods. So insulin is going to negatively regulate blood glucose. That means it's going to lower it. It comes from the beta cells in the islets, and a lot of times we see insulin being released after we eat something with like a lot of carbs, right? Because if you eat a lot of carbs, right, there's gonna be a lot of free glucose in your blood from you eating that. And the whole point of insulin is to lower your blood glucose level back to normal, especially after like a meal where you've just had this event where you've raised your all over like your nutrients, right? You've absorbed a bunch of nutrients. They're in your bloodstream. You got to put them somewhere. They can't just hang out there forever. And so insulin is going to help with that. The way that insulin helps cells is that it is going to, if we look here, remember these RTK, these receptor tyrosine kinase receptors. So remember, insulin binds. These guys come together to form a dimer. We autophosphorylate. We send out signaling molecules. But the whole point is so that these vesicles with these glucose receiving channels, right, what we call GLUT4, right, these channels go from inside the cell out to the membrane, and then once they're there, we basically opened the door for glucose to get inside the cell, right? And so we see this in fats, we see this in muscle, we see this in liver tissues, right? And then when that signal's gone, right, or when glucagon comes along, right, we can then bring these receptors, these channels back in. Whereas glucagon, it's antagonistic to insulin, meaning it works opposite. It is going to positively regulate blood glucose, meaning it's going to raise it. These come from the alpha cells when blood glucose is low. Again, if your blood glucose level is very low, we need to go back up to normal. So how can it do that? Right, one, we can stop absorbing glucose into the cells, but also stimulate the glycogen breakdown in the liver, stimulate the production of new glucose molecules, stimulate the breakdown of fats, right, come from glucagon. So if we look at how these two kind of act side by side, number one here, we have low blood glucose, right? So this would be like you haven't eaten in a while. Maybe it's been hours since you last had a meal, and so your blood glucose is going lower. That's where glucagon comes in. We convert glycogen to glucose. We form glucose from lactic acid or amino acids. So gluconeogenesis. We release that into the bloodstream. Blood glucose levels go back up, right? And then once we reach a certain point, right, once our blood glucose levels are back to normal or on the high end, it's going to basically tell glucagon to stop. From there, right, let's say we're too high, right, we're hyperglycemic, our blood glucose level is too high, maybe we just ate a meal, right, whatever. Now insulin gets released. Insulin is going to allow cells to bring glucose in. It's going to take glucose and convert it, or help promote the conversion to glycogen in like the livers. We're going to take up amino acids and build more proteins. We're going to build fatty acids, right? So we're going to build fats, blood glucose levels fall. And then again, if it goes too low, that is going to inhibit insulin, and back over here to the start, right, glucagon gets released. And so this is another teeter-totter, another seesaw one, kind of like what we saw with calcitonin and PTH. We see these two hormones that are antagonistic to each other that work opposite to always maintain something that's relatively in the middle. But what happens when that control is lost, right? This is where we have diabetes mellitus, or diabetes for short. I'm just going to call it diabetes. Diabetes is basically we don't have the ability to control blood glucose anymore. This results in hyperglycemia, and there's two main types, at least for diabetes mellitus. So we are not including in this list, right? We are not including diabetes insipidus, and we're not necessarily including gestational diabetes right here. We're just going to focus on these two types, type 1 and type 2. Type 1 is what we would know as insulin-dependent diabetes. Sometimes also we hear things like juvenile diabetes. This is not very common. Typically, this is an autoimmune disorder where the immune system attacks and destroys the beta cells in the islets. And remember, beta cells make insulin. So a person with type 1 diabetes, part of their pancreas no longer works because their immune system has attacked it. And so because of that, they cannot actually make insulin. So someone with type 1 diabetes absolutely needs to have insulin through pharmaceutical means, right? They have to give themselves injections of insulin to regulate their blood glucose levels. So it is something that typically pops up. We know that there are, because it's autoimmune, there are some genetic factors that come in. There are maybe exposures to certain viruses that can trigger that autoimmune response. But typically when we see type 1 diabetes, we're looking at someone who's usually diagnosed in either childhood or early adulthood. So people with type 1 diabetes are generally diagnosed relatively young. If someone with type 1 diabetes does not control it, right, if they don't have access to insulin, this will eventually kill them. So it can cause damage to the cardiovascular system, it causes damage to the renal system, it causes damage to the nervous system when someone does not have the ability to care for their type 1 diabetes. And again, the care for type 1 diabetes is insulin. Type 2 diabetes, or insulin independent diabetes, this is the one that you usually think of when you think diabetes. This is the one, it's way more common. Most of the time if someone says they have diabetes, they're probably talking about type 2. And the issue with type 2 diabetes is that you're still making insulin. The pancreas is still working, but the cells in the body are not listening to the insulin signal anymore. So insulin is still there, but we may need to add more insulin on top of what's naturally being produced to make the message loud enough, right? So remember that insulin, right, it binds to that receptor, and then that causes the glucose channels to go out onto the membrane. Basically, like, the insulin's there, it's binding, but we're not, everything on the inside of the cell, like adding the carrier proteins to the outside of the cell to bring in glucose, is not happening. The cell's like ignoring the signal that's there. Type 2 diabetes is very strongly correlated with things like lifestyle factors and genetics. So whether or not it runs in your family, also does that person, people who have a sedentary lifestyle, right, they don't really move much or exercise much, people who have poor diet, people who are overweight, obese, or morbidly obese, right, are at higher risk of developing type 2 diabetes compared to someone who's not. So there are things that go into developing type 2 diabetes, and typically type 2 diabetes, we're looking at someone who's at least 45 developing it. That being said, it is becoming more common including at younger ages. So we are seeing people who are showing signs of being pre-diabetic or even full type 2 diabetic in their 30s, sometimes even 20s. So it is a major issue. It is a major health concern in this country, and a lot of it comes down to how we move or the lack thereof, and what we eat.